Understanding the role intermolecular forces play in chemistry is a traditional hurdle for students. Specifically, creating mental models of the types of intermolecular forces and understanding the dynamic interplay of molecules as a consequence of these interactions requires dynamical models that are highly visual, adjustable, and of course, chemically correct. The next series of videos shows 3 experiments from Odyssey Molecular Explorer. In these simulations, we show various ways to visualize intermolecular forces and explore how these interactions impact a collection of water molecules, both in terms of dynamics and important physical properties.
For students to really get a good grasp of how intermolecular forces affect the structure and dynamics of a collection of molecules, we first have to understand how we can visualize the asymmetry of electron distributions for an individual molecule. And this is what Lab 63, visualizing the molecular polarity of a water molecule, does for you. So what we have right here on the left is a sample, a ball and spoke representation of one water molecule, effectively its own little universe. It's the only thing in our little computational universe on the left. And what we'd like to do is to use quantum mechanics to try and visualize the polarity of the molecule. So of course the job of quantum mechanics for us as chemistry teachers and as students is to give us an idea of the distribution of electrons around the atoms in a molecule, or the atoms themselves or a molecule themselves. And fortunately, Odyssey provides several tools to help specifically with that visualization. The first of which is what's known as the outer surface of electrons of a given system. And so if we go to the menu bar and look at the electrons tab on the menu bar, I can collect on outer surface. And what this shows is what we would consider an electron density map. This particular surface shows a volume in space where we could effectively say all the electrons are in a water molecule 90 to 95% of the time. So if I wanted to draw a 3-dimensional shape around a water molecule that would tell me where the electrons are approximately 95% of the time, it would be this shape, which has been calculated from quantum mechanics. If we notice, this shape almost looks spherical. It's interesting that it doesn't have a lot of asymmetry, but we can tell that it is localized. It has almost the traditional Mickey Mouse shape that we would associate with the water, almost a little triangular shape right there, that indicates the fact that the water molecule, say, is it's not linear, it's not bent at a 90-degree angle, that the details of this electron density shape are because of the bond angles within the specific nuclei of the molecule. But unfortunately, although this shape does give us information about the electrons as a whole, it doesn't give us the specific information about the distribution of electrons we need to understand the polarity. And in order to do that, we have to basically refine this shape slightly and generate what's known as a polarity map, which in some cases is also known as an electrostatic potential map. And what this does is add another layer of calculations to the quantum mechanical description of the molecule that allow us to see how the distribution of electrons is symmetrized or has asymmetric properties on one side of a molecule versus another. So if we go to the polarity map itself, what we're now seeing is a representation that shows us how symmetric or asymmetric the distribution of electrons is. And what we see from the polarity map is that the oxygen side of the molecule has a much higher density of electrons over the long term than does the hydrogen side of the molecule. The electron distribution is asymmetrically skewed towards oxygen as it is relative to hydrogen. And this is what quantum mechanics tells us for the water molecule. The oxygen side of the molecule is slightly more negative than the hydrogen side is over the long term. The electrons distribute themselves more frequently so that they have a higher probability of being found on the oxygen side of the molecule relative to the hydrogen side of the molecule. We represent this complicated quantum mechanical calculation by a simple color. So areas where the electron distribution is skewed towards higher values, we color those as red. Where the electron distribution is skewed towards lower values, we color that area as blue. So this is our quick and easy representation of trying to say, hey, the distribution is asymmetric, and it's asymmetrically oriented so that the oxygen side of the molecule has a higher probability of finding electrons around it over the long term relative to the hydrogen side of the molecule from right there. We can do this for any molecule, but the most important thing here is seeing that this asymmetry really indicates to us that the oxygen side of the molecule is negative and the hydrogen side of the molecule is positive. Now, there are other ways to represent this in a more classical sense. We can actually put some numbers to this asymmetry of the distribution by looking at what are known as atomic charges. So if we really want to put a number to say how much more negative is the oxygen side of the molecule relative to the hydrogen side, we simply can do that. To make the numbers a little more visible, I'm going to go to the ball and wire representation, and then under style, I'm going to go to charge labels partial atomic. And now what we're seeing here is that we're actually giving a numerical value to the excess negative charge around the oxygen molecule relative to the deficit of negative charge around the hydrogen, the oxygen atom, relative to the lack of negative charge for the hydrogen atoms right here. Notice that the partial charge for the oxygen atom is negative 0.644, whereas the partial charge of the hydrogen atoms is each 0.322. It's important to note that the total sum of the charges must add up to 0 because water is electroneutral. The number of positive and negative charges in the molecule of the whole is the same. So therefore, since we're just looking at an asymmetry in the distribution of the electrons, the total amount of charge must add up to 0. So therefore, it's not surprising, given the symmetry of the water molecule, that each of the hydrogens takes up half of the deficit of electrons, while the oxygen atom gets the full excess of electrons due to the asymmetry of the distribution. But this allows us to quantify things a little bit more in terms of the charges. And we would have expectations that molecules that experience greater dipole moments, molecules that are more polar, would have a greater partial charge separation or partial charge values for the different atoms in the system. Another way to represent this as well, to kind of remove some of the quantitative nature of the numbers, but still maintain the idea of the positive and negative nature without having to draw the polarity map, is to add in a dipole arrow. So if we go to style, we can go to the style menu and add a dipole arrow from right here, and we will see the dipole arrow is a traditional way of representing the positive and negative side of the molecule. Per IUPAC standards, the head of the arrow represents the negative side of the molecule, whereas the tail represents the positive side. And in addition to that, the arrow is lined up to maintain the symmetry of the dipole itself. So although there are two areas of electron deficit in hydrogen with each 0.322, the average location of that deficit would be right down the middle, which is the tail of the dipole arrow, where the negative side of the arrow, the negative 0.644 charge, would be represents the head of the arrow as well. So even if we do not want to go as quantitative with partial charges, or we don't want to go as quantitative with quantum mechanics and look at a distribution of the electrons as a whole, we can still get a nice picture for the polarity of the molecule itself by just using the dipole arrow itself, telling us that, hey, where the head is the negative side of the molecule, and where the tail is the positive side of the molecule as well. Dipole arrows are specifically valuable when we're looking at large collections of atoms and large collections of molecules, because in those cases, when we have a molecule with many atoms in it, doing the quantum mechanical visualization of those is very complicated and very computationally time-consuming, whereas the dipole arrow kind of gives us the snapshot of that picture very quickly. We will see throughout many different visualizations that all three of these different pictures, partial charges, dipole moments and dipole arrows, and electron cloud distributions, will all be used to represent the polarity of a molecule, and one must choose the best representation depending on the situation and the dynamics they're looking at for a specific discussion and simulation.